Thank you so much, everyone, for being here. It's a fantastic privilege to be able to meet you today, and it was a truly humbling introduction. So thank you so much to all the esteemed guests who've made our visit so welcoming. I'm sorry for catfishing you. That is quite an old photograph of me. I'm slightly older now. What I wanted to do today was cover the ethos of how we teach civil engineering in the UK. So I know there may be members of the audience who are interested in EEE, electronics and electrical engineering, but I'm from civil engineering, so I'll concentrate on that. What I would like to do is give an example of where my career has taken me. So a career in civil engineering from the UK can almost literally take you anywhere. So to start with, what I will talk us through quickly is one of our flagship programs, the Structural and Fire Safety Engineering program. And we like to say that structural and fire safety engineering is like structural engineering plus. And the example I can give you is if you build a chimney for a fireplace. How you design that chimney will very obviously affect how that fire behaves. So you cannot understand how fire behaves without also understanding how the structure behaves. As that structure evolves, the fire behaviour will change as well. So you cannot separate fire engineering and structural engineering. So that's why we have the structural and fire safety engineering program. As I said, then I'll talk through what my career has allowed me to do. I will go through what we have discovered as part of our research. I'm an unsaturated soils mechanicist. So can I get a hands up, everyone who's in civil engineering? No one. No one's in civil engineering. One break, great, thank you. So this would be a benefit of at least one person. Fantastic. But then, why am I telling you some theory? The point will be the theory is very, very specific. This is for soil stabilization. It's a very important issue in environmental geotechnics. But I'll show you some projects that I won't spoil the surprises. I'll show you the projects I've been able to work on because I'm an expert in soils, and you'll be quite surprised that none of these projects have anything to do with soil. So I wanted to start with what is civil engineering. We are accredited by the Institution of Civil Engineers. I'm a chartered civil engineer as well as a Doctor of Engineering. And this is what we do. So civil and environmental engineers design, create and connect the world around us. That is the definition offered by the ICE. My own definition, we are the inventors, innovators and practical problem solvers that place humanity's stamp on our planet. In 500 years' time, no one is going to understand what an iPhone is. No one will be able to detect a Wi-Fi signal. But everyone will see buildings, roads, palaces, schools, drains. That is the civil engineer's role. We control, that's why it's civil engineering. We create and maintain civilization. But it is also our responsibility to do that ethically, appropriately, morally, and the best way that we can. Very briefly, how do we attempt to do that in Edinburgh? Our degree comprises 5 years. I'll do this quite quickly. In the first year, we go through fundamental principles. I assume you do the same. Well, in fact, I know we do, because we had a look at the curriculum yesterday. And then we take you through all sorts of engineering science. So we start with mechanics, structural mechanics, soil mechanics, fluid mechanics. I'm sure the civil engineers in the room are very familiar with that. You learn how materials work, then how structures behave and how to analyse structures. Then, because we're civil and environmental engineering, we look at environmental engineering. We look at aspects of water treatment, because a building in isolation is rubbish. There's a story from ancient Greece and ancient Rome. The ancient Romans conquered ancient Greece. And they looked at the Greek buildings and said, we like these, they're great, but they're not connected. So if you look at a Greek city, there are wonderful looking buildings with no infrastructure. A Roman city looks exactly the same. But there are drains, there are aqueducts, there's infrastructure, everything is connected. So again, to make that holistic, environmental engineering, and water treatment. How do we get people actually to live in structures that we build? As a civil engineer, always remember that. The function of the building is the most important aspect. Yes, it will stand up, hooray, but if no one can use it, the building is pointless. So we look at engineering construction. How do we actually build things safely and effectively? Transport engineering. How do we actually get to the buildings that we are building? And finally, hydraulic engineering for the more technical aspects of power supply from hydroelectrics, from the plumbing side. In all of this, and in all the work that we do, and you do as well, we know this, we embed ideas of professionalism, leadership, and ethics. What I'll talk about briefly, though, also are specialisms. How can you choose what to do? Because civil engineering is a very broad church. What can you do inside civil engineering to make yourself a special civil engineer? Of course, that's based on mathematics. There are very strong elements of design and sustainability. Now, here's a quiz for you. This is mostly to wake me up rather than you, because I'm still quite horribly jet-lagged. But what I want is a show of hands. Who thinks there is such a thing as a sustainable material? So if I can say like concrete, fibre brick, timber. Who thinks timber is sustainable? At least one brave person. Come on. Timber is sustainable, low carbon, can be grown, can be harvested. What about concrete? Sustainable. Like it. Fibre brick? It's a trick question. There is no such thing as a sustainable material. There are sustainable contexts. Concrete is, people try to say we should use less concrete. Concrete is essential for many tasks. For example, the foundations of a building. The civil engineers, the senior civil engineers in the room will be doing foundation engineering. Part of the operation of a foundation is to be a very heavy thing at the bottom of a building. That's what stops the building falling over. If I didn't use concrete, what else would I do? That's its role. If I build a timber structure, people might say that itself has very low embodied carbon. Great. What if I built that timber structure on the moon? It's still the same structure, it's the same material, but now it's not sustainable. So there's no such thing as a sustainable material. It must be assessed in context. And we embed that in every single year of our 5-year program. That gives us ideas of being able to judge a design. It allows you to generate ideas, work on communication, because you're trying to pass those ideas on, and get that independent learning and development that is necessary for an engineer. Another thing we said the other day is that if you only follow code, you're a computer. That's what computers do. If you're appraising code, you're an engineer. You must understand what the code is trying to do. I don't necessarily just mean computer code. This is also standards, codes and regulations. What are they trying to do? A code and regulation is a simplification of a very complex problem. Those simplifications will have assumptions behind them. It's the job of the engineer to identify those assumptions and understand if they are appropriate. Let's say, for example, you look at a batter angle for a cliff. Someone mentioned this yesterday or the day before. And someone says, no, the angle must be less than a certain amount. I say, okay, why? Well, because the rock isn't very secure. Yes, but in this design, they've put rock bolts in. So I can change the angle. If you purely go by what the code says, you'll find out that you're not actually engineering. You are just following code. I'll go through this one quite quickly. I mentioned specializations, and I mentioned the structural fire safety program that we have. As I said, it's structures plus. So we have fire safety engineering, but also how to test in a laboratory. Certain items act very differently under extreme temperatures, and controlling the temperature is very important. We have structural design for fire, and numerical modelling for fire. So all the tools that you need to get that holistic view as the engineer of how a fire works. Just so I can tick the box and say I've shown these characters. Our fire safety engineering program, and this is of interest for anyone who wants to do an MSc, is led by two of the world's best fire engineering academics. He's the best in the world, which means that he can't be because he already is the best. So he's the second best. They are the leaders in all national fire inquiries in the UK. They're world authorities on fire performance for structural design and structural strengthening, and also world authorities on the spread of wildfires. Really critical issues. I know there was a wildfire here a few years ago, spread by pine needles. The research on how fire spreads using pine needles is Professor Happy. I also said we're civil and environmental engineering. It's how is civil engineering interacting with the environment. One more missing. So we also look at how to use civil engineering to extract energy from the surroundings, and how does that affect how a building behaves. We call that energy geostructures. We have building energy and performance. So this room, lots of people, lots of sources of heat. How can we design the room so that it can cope with that thermal load? Structural design for earthquakes, something that's very close to home here. How do we do that? How do we repair structures, and how does that affect how that structure behaves? If I had a concrete beam and the beam has cracked and I wrap that beam in FRP, fibre reinforced polymer, I change the stiffness of that beam. That means I must change the load path in that structure, because load always follows the stiffest path. If I've changed the load path around the damaged element, then, well, that's not going to help, because now I've directed all the load into the damaged element. So we need to know how the structure behaves holistically. And we've also got the world, literally, the world's experts in using ground-penetrating radar to detect infrastructure or anything. So when Google has a problem about how to use radar, in this case most recently on Mars and on the Moon, Professor Giannopoulos in our school is the one that they go to ask questions. Just some examples of tasks that we're working on in the UK. Something I should stress is that University of Edinburgh, we graduate, so 96% of our cohorts leave to top-tier jobs. 4% do whatever they want. But we send our graduates to every leading consultant. And so here are some of the projects that are being worked on. Lower Thames Crossing is a new one, led by Jacobs. Northern Rail, Arup, Mott MacDonald's and WSP. And if you're less interested in transport, we have reservoir projects under Coffee and GHD. We also have engineering contractors. So if you're more interested in the construction side, we still have engineers embedded in these companies as well. Balfours, Skanska, Atkins Realis, Amy, and Macleay. Anything is possible. All of these sectors are open, and our graduates go into every single one. As I said, I can't really take you through an average career because there isn't one. So I will relatively quickly go through my own career. So I did a degree in civil engineering. I graduated from the University of Durham, so that's me. It's a tradition to put the hood up over your head and have a photograph, because behind us is the building where they filmed Harry Potter. So everyone puts the hood over their head. So 2004 to 2008. Then I applied to Arup and Schlumberger. So Arup is a big engineering consultancy. Schlumberger is an oil exploration company. And I got the offers from both. And a week later, my master's thesis supervisor asked if I wanted to do a PhD. So I said, yes, please. So I didn't do that. So PhD 2008, 2011. And then I applied to Arup again, and they said yes. And then someone from the University of Western Australia contacted me and said, your PhD is in unsaturated soil mechanics. Do you want to come to Australia? Yes. So there I was. So I didn't do either of those. Again, Arup hates me now because I've had to reject the guys. go to Western Australia for 5 years. And then there was an academic position available at the University of Edinburgh. So I went there. I was very fortunate. I passed the interview for the academic role, and I became a lecturer in 2017. I'm now a senior lecturer. I'm the degree program manager. I'm also the deputy director for civil and environmental engineering, which is how I have the privilege to come here to talk to you today. That top banner, sorry, I should just say, is a selection from research I have done since. So, PhD focused on materials science affecting soil. And then we just looked at what does that mean for how does soil behave. So I'm going to go through something which is hopefully very relevant for you guys, which is soil stabilization. This is a very, very common practice in geotechnical engineering. And it's very, very easy to get it wrong. So we'll just go through how this works, following the rules that we have developed from our research. Why would I want to stabilize a soil? We stabilize soil to reduce swelling, to increase the soil's shear strength and the bearing capacity. Hopefully you know this already. The stabilizers improve physical, mechanical, chemical properties of the soil. And we use low stabilizer content, maybe 2 to 3% of the soil dry mass. But we're geotechnical engineers. We deal with projects that have millions of cubic meters of soil. So this can be thousands of cubic meters of stabilizer, of cement or of lime that we're trying to commit to these soils. And we need to know how to optimize that stabilizer performance, because if I can reduce that 3% to 2%, I have saved millions of pounds. But to do that, we need to know how it actually works. So what are the soil stabilizers that we could possibly think about? We have cement, and hopefully most people know how cement works. It reacts with water. Everything else is chemically available inside the cement. We could use lime. Lime contains half of what is needed for a cementitious reaction. Lime needs to react with clay. Lime and clay together at a high pH with some water will also create a cementitious reaction. It has a lower carbon content than cement. It's roughly half, but it's not zero. So lots of people say lime is very environmentally friendly. It's more environmentally friendly, but not really that good. Alkali activated is a very contentious one, because as far as carbon is concerned, you can take some precursor materials. So for example, fly ash and blast furnace slag. These are wastes from the steel industry. So with tartar being very strong here, there probably is a very good supply of these waste materials. But we need to mix them with an alkali activator, either sodium hydroxide or sodium silicate. Those have an incredibly high carbon cost because they have to be manufactured. So although it uses waste materials, alkali activation is just as bad as using cement, but less certain because there's less quality control in the raw product going in. And something new coming online is biostabilizers, using bacteria that precipitate calcite to bind a soil together from within. That's possible, but the theory I'm going to go through in the next, say, 10 minutes will show you why it's very difficult to predict how this is going to work. So I'm going to go through what I've called 3 inconvenient truths about soils and how they work when it comes to being stabilized. First problem. Stabilized soils are granular. They follow the rules of granular mechanics, not continuum mechanics. If you've written an equation, x plus dx equals something, that is continuum mechanics. Soils don't work like that. Problem 2, stabilized soils are unsaturated. You don't get a big block of soil with cement and it's just full of water. That's not how it works. They're normally stabilised because they're near the surface. That's where we need the extra strength. Soil is already strong at depth. That's how friction works. We're interested in the shallow soil. It's unsaturated. And we have a very low stabiliser content. I mean, we can't guarantee where it is. We don't know if we're sticking all those particles together or not. So granular materials, they follow the rules of friction and overburden. What do we mean by friction? Oops, sorry, one of those was an animation. It is. This is all to do with force chains. If I load a granular material, the load will follow a certain path. Some of those particles are not loaded. Some of them are. When you see later the distribution of stabilizers, bear this in mind. If this is the load path here, these red lines fading to yellow with less load, but all of my stabilizer is up here, then let's say I've stabilized 1/3 of that diagram. I've used a lot of stabilizer, but I've achieved nothing because I've made this bit stronger, and it's this bit that's loaded. So that's a complete waste of stabilizer. You could say, yes, the code says I must mix 1 bag of cement into 10 bags of soil, or usually 1 bucket of soil from an excavator. I'll mix 1 bag of cement in. Have I done it? Have I worked according to code? Yes. Have I worked according to engineering? No, because you only mix this bit, and this bit is the bit that's actually being loaded. That's the bit that will fail. This is taking you back, hopefully, to your 2nd year or your 3rd year. Granular behaviour also means materials act in a dense or a loose way. If the particles are as close together as they can possibly be, and then I cause them to move, they must move apart. They're already locked in place. So that will dilate. A loose material, if I try to make those particles move, they can fall closer to each other. So that material will contract. So I have lots of volume change going on. That will give me different strengths. So if an engineer or if a contractor says, I need a soil of a certain strength, that's absolute gold dust to a geotechnical engineer, because all I need to do is confine that soil and then test it, because it's frictional. If I combine the soil, I get this peak strength, which I can report as the strength of my soil. The actual strength is down there. That's the residual strength, after everything's sort of started moving around and reached an equilibrium. So again, code says, achieve this strength. Engineering says, I have lots of ways to achieve that strength. You've also seen diagrams for drained behaviour. We have effects of cohesion to worry about. That can also arise from cementation. And a stabilised soil will always act in a drained way because it's unsaturated. Hopefully you remember the difference between drained and undrained. Undrained is that the water, as you load a soil, the pore pressure goes up. That counteracts the effect of overburden, and your soil effectively tries to float. This is called liquefaction or piping. That's how buildings often fail in earthquakes, if there's a ground failure, not a structural failure. If it's unsaturated, that pore water pressure cannot build up. The water can just move. There's air in the way. So it's always going to act in a drained way. We have to think about how the soil is going to behave as it is loaded. Is it going to contract or is it going to dilate? I've already just said this, so I'll go through that quite quickly. I don't want to take too long. Problem 2. These soils are unsaturated. So we have issues of granularity and friction, but we also have issues of suction. This is the phenomenon when there's a small space in something that will naturally cause water to move through it if that space is hydrophilic. This is the main core of my research. These are 2 glass beads with some water between them. That water will always form a bridge between those 2 beads. That bridge, if you do some maths, has a lower pressure than the air around it. And that means those 2 beads are sucked together. So I'm not applying friction by pushing the 2 grains together, but I am applying friction by pulling the 2 grains together from the inside. So this has the same effect as placing a load on a soil. It acts to lock the particles together, so the strength increases. Now hopefully, though, some of you are thinking, okay, it increases, but by how much? And the answer is, it depends how much water there is. So if my unsaturated soil is exposed to rainfall, as a real stabilized soil is, then there's more water, the pressure difference reduces, and the soil strength goes down. I didn't change the soil. I didn't change how much stabilizer there is. I just made it more or less wet. And now I have half or less the strength I originally had. You know this if you've ever made a sand castle. If I tried to make this and it was too dry or too wet, it would just collapse. It has to be damp for it to stand up. For those of you who want to have maths in slides, here's some maths. This is a capillary tube, and what we have is the radius of the capillary in the tube. We have the radius of the tube, capital R, and this is the Laplace equation. Gamma is the surface tension, and because of surface tension, the pressure in the liquid goes down, and the capillary will rise up in the tube. If the tube was hydrophobic, so it tries to repel water, that meniscus would move down. It would be in the opposite direction, and it would move down to counteract the pressure difference. The smaller the capillary tube, the higher it goes, because little r goes down, which means pressure difference goes up. That means it must move higher to counteract the pressure. In 2D, almost exactly the same. We have two different curvatures. I've labelled them kappa and L. We have some other angles that we can define, but basically the same principle. As this radius reduces, these two particles are brought together more tightly. As the radius increases, we have more water, the particles are released. We have something called the soil water retention curve. So if we start off with a soil which has a lot of water in it, and I start to drain the water out, just like the capillary tube, the big pores empty first. So I apply a little bit of suction, and I have a degree of saturation, which is the amount of water in there versus the void space, close to 1. As I apply more suction, I remove more water, because I'm emptying the smaller pores, so the amount of water in there must go down. So low suction, I have some value, medium suction, a lower value, and a high suction, a lower value still. This is important because what do stabilizers need to react from the first slide? Water. So if I've removed the water from my stabilized soil, my stabilizer isn't going to react. I will just have a particle of cement waiting for water. It hasn't done anything. Another issue is that this process is what we call hysteretic, which means that if I change my direction of wetting and drying, the two curves don't overlap. That's because of some surface physics I won't go into. What we also have, and we've checked this, we said that there's that effect of the particles being brought closer together or not. That changes the strength. And again, you might be saying, well, how much? This doesn't sound very important. It's just a small bit of water. This is a test on a compacted soil from a paper we did in 2018, where we controlled the amount of water by changing the humidity that the material was exposed to. And the strength changed by 50%. Now, as an engineer, anyone, electrical, civil, mechanical, a material that changes by 50% of its strength just by changing the atmosphere which it sits in should be absolutely terrifying. 30% relative humidity is kind of like what it's like outside today. It's quite dry. 90% might be monsoon season. 15 to 40 degrees, I think that's the temperature range just today, to be honest, which I'm not very used to. But you've got a material that in the course of one day could improve in strength by 100%. And then at night, lose 50%. So your factor of safety, if you're following code, has gone from 3 to 1.5 to 3. And you think, yeah, I designed that building really well for seismic design. I have a factor of safety of 5. Great. If I test it at lunchtime, it's now 2.5. And it's back to 5 again in the evening, or the other way around, depending on which country you live in. It's also affected by how much clay is in there, because this is all to do with surface chemistry. So lots of issues that we've identified. What we can do is plot that in 3 dimensions. So the red and the blue are your standard Mohr Coulomb surface, which I'm sure most of you know. We add a third axis, the green one, which is our suction, which is given the symbol psi, and we can create a surface. And this allows us to predict how one combination of net stress, sigma minus UA, and suction might land on that surface and reflect it back to what the strength of the material is. I might say, oh, I've got another material which is at a higher confining stress. Now, traditional soil mechanicists would say, great, higher net stress. Therefore, because the friction angle is positive, it must have a higher shear strength. Job done, go home. The unsaturated soil mechanicist says, hang on, there's a third axis. What's going on there? And in this example, the suction is much less. So we track that up to the surface, we find ourselves here, we track that back over here, and our strength is actually less. We increase the confinement. Under traditional Mohr Coulomb, that should be a stronger soil. Under extended Mohr Coulomb, the work that we do, it is not a stronger soil. If you hadn't been told that today, you would have probably thought about that. But any geotechnical engineer should be aware of this. There's also changes in the stiffness. So anything to do with earthquake design. As I take these materials through cycles, and as I change the suction, there is a change in the maximum strength achieved, and there is a change in the stiffness achieved. I won't dwell too long on this. How long have I got left? 0 minutes, probably.
10 more minutes.
10 more minutes, fantastic. We've also got the ideas of compaction. Now, I know you guys have done compaction in your soil mechanics course, possibly a geotechnical engineering course. But now we're thinking about why is compaction, not what is compaction. This is a soil mixed at a low water content. The soil is a general mix of clay, silt, and some sand. If I do that and then make a ball of the material and just drop it on the floor, it will look like this. And the microstructure, again my speciality, looks a bit like this. You've got some big particles, which are the grey ones, and some aggregates of small particles, which are the white ones. If we zoom in on the white one, we've got some smaller particles in there still. Those are our silt particles. And we have some clay packed in between them. At the other end, if I compact that material really wet, lost some pictures there. Oh well, we can still work with it. So the picture that should be over here, for some reason has disappeared. But it's the same thing. If I mix the soil wet, pack it into a ball and drop it on the ground, it'll just be it will just stop. Its microstructure looks like this, big aggregates with the little particles sort of embedded inside. And in the middle there's an optimum. So that is where I drop it and it breaks into some fragments. And it's a mix. I have some large aggregates, some small aggregates. This is the compaction curve that hopefully you guys have seen. What's going on? This is the side with the aggregated structure, and this is a more, what we might call monolithic structure, a matrix structure, sorry. You guys are welcome to have the slides afterwards. I've just said in words what is written here in case the microphone isn't working. So as a summary, how unsaturated soils strongly control how the soil actually behaves. And that is a function of how those particles are arranged. Now hopefully, because I spoke about stabilizers first, you're now thinking, hang on, if how the particles are arranged affects how the soil behaves, and how wet they are affects how the soil behaves, how does that affect where the stabilizers are going to be? That's the next problem. Our stabilizer content is not big, it's small. And that affects the choice of stabiliser, the friction, the overburden, the curing time, and the suction. So if I have two mixes here, people always wonder, that's also not quite come through, people always wonder why a stabilised soil doesn't look like concrete, and also why they can't use the rules for concrete to stabilise soil. So here's a typical mix. That's an M10, that's a weak concrete. 100 kilos of cement, 300 kilos of fine aggregate, 600 kilos of coarse aggregate, and 42 kilograms of water. You've all seen concrete. It's a fluid. You pour it into a box, it sets, everyone's happy. For a soil, 50 kilos of cement. Okay, so only half. 600 kilos of fine aggregate, 400 kilos of coarse aggregate. So the same-ish mass distribution. 100 kilos of water. So surely this is going to be twice as wet as the concrete. No, it's not. That's what stabilised soil looks like. Basically still dry, like soil after rainfall. It's not going to flow anywhere. You think, hang on, but I've got more water in this one than this one. Why is this one dry and this one's wet? That's because in concrete, the aggregate is wet. And in soil, the aggregate is dry. So all of this water reacts with the cement. This water gets absorbed by these two. So there's much less to react with the stabiliser. So being in control of where that water is, which is unsaturated soil mechanics, tells you whether you're going to get a high strength or a low strength from the same amount of stabiliser. In concrete, we can guarantee all of that stabiliser works, because all of the water is used to hydrate the stabiliser. In soils, not true. This is where the stabiliser ends up, based on our previous microstructure diagrams. Stabiliser, when you first use it, is a particle. It obeys the rules of particle mechanics, granular mechanics, and soil mechanics. Those particles in a material compacted dry will be isolated. They have the capacity to stick lots of these particles or aggregates together. If I compact it wet, the stabiliser, the black dots, is inside that matrix structure, which means it can stick the stuff around it together, but nothing is sticking this bit to this bit. Nothing sticks this bit to this bit, and this bit missed one entirely. At optimum, we have a distribution of both. We have some stabiliser that's ineffective, and some stabiliser that is effective. Now, you know from road design, from geotechnical engineering, we always try to compact to 95% of Proctor. The code will tell you, compact to 95% of Proctor. If it's a stabilised soil, do you think that's a good idea or not? General murmuring is fine. It is not, because this is the effective stabiliser. This is less effective. This is not effective. So if I compact to optimum, this one, I am less effective with my stabiliser. The whole point is to get strength out of the stuff. But by compacting it, I've made it worse. Here's some numbers. I've left the actual numbers off, but this is to scale. Same amount of stabiliser, same soil, compacted dry of optimum, achieve twice the strength as the same soil compacted above optimum. Tested at the same value of suction. If I change suction, of course, those bars will move around as well. So it's really critical. Now we're talking, as I said before, if we want to reduce that 3% stabiliser down to 2%, I can, if I understand this. And I understand how unsaturated soils work. And I understand how Moa Coulomb works. And I understand how confinement works. Here's the alternative. I followed code. I compacted any soil to a stated dry density. Okay? These exist on compaction curves. Here's one of them, but here's another one, and here's another one. So some of them were compacted dry, some were compacted wet. So they might end up something like that. Not doing what you wanted, even though you compacted them to the same density. Because the distribution of the particles was different. The compacted effort was different. There's also issues with if you leave the stabilizer. So I add the stabilizer, leave it for a few hours, and then come back. Well, now it's started reacting. That's going to affect how big those aggregates are, because it's sticking more particles together. But that's good, right? Well, maybe, unless it was encapsulated in the matrix, then it's not doing anything. So lots of other concerns as well. I will, I think, I'll go right to the end on this. Until a certain point, nothing happens. This is totally wasted. Then, as the cement content increases, the strength goes up. In this one, I've only got about 5 minutes left, but probably actually less. As I add lime, the strength actually goes down until hitting a fixation point. Then the strength starts to go up, but not as much as cement. Lime is never going to get you that high strength. That's my expertise. That's work. What did that let me do in my career? My first project was building low-energy housing in a desert. Why? Because they used soil-based walls, so they're called mud huts on camp. We call it rammed earth. Rammed earth is brilliant in arid conditions, like a desert. So we built and monitored low-energy housing in a desert for 5 years. In a collaboration, it's a 2 million project, collaboration between engineering, computer science, and the government. Hello? Oh, no. Second project. You're an expert in unsaturated soil mechanics. What's your project? Learning how the Romans built their frontier. Because they built it out of turf. Turf is a mixture of soil and roots. To an engineer, that's soil and reinforcement. So we completely redefined the archaeological understanding of how the Romans built structures. Why do we care? Well, we can still do this. It still stands up, it still works. So we can use these natural materials to build boundaries. Third project. You're an expert in unsaturated soils. What are you doing? I'm looking at how to make houses in Madagascar resilient to cyclones. Why? Well, because it's attached to the ground. The lateral capacity in a cyclone comes from the embedded column in the ground. The structure needs to be reinforced, but we must understand the consequences on the ground. Another £2 billion project. Last problem. You're an expert in unsaturated soils. What do? Let's look at social housing in Brazil. And we'll look at combining mine tailings with soil. This is brilliant because the local soil is acidic. We cannot put steel reinforcement in an acidic soil, it will corrode. Mine tailings are not acidic, so if I mix the tailings into the soil, I increase the pH. That makes it easier for cement or lime to react, and then I can protect the reinforcement. So looking at that as another Leverhulme project, number undisclosed, supporting a PhD student for 3 years. And I wanted to finish, well, I'll finish with a slide of my collaborators, but finish with something I took from your website. I believe, and you believe, that a great university drives cutting-edge knowledge and innovation while working for the social and economic upliftment of the community at the same time. And I hope that my project, building on soil mechanics, looking at low-energy structures, sustainable frontiers, the middle one, which I can't remember, Madagascar, and this one in Brazil, shows how we as engineers, as trained engineers, can contribute to this economic uplift and the community. These are some of the wonderful people I've had a chance to work with. In your career, you get to work with a raft of people as well. I'd like to thank these funders for covering all the work that we've done since mostly 2018, and thank you very much.